It's good to see you. Hi. Yeah, we missed you last time, Om. Where were you? Uh, I was late. Om is always late. Om is late all the time. It's a real problem. Om, you shouldn't be late. Snow, it's okay. It's okay, Snow. It's not okay. Om is late. Snow, we all have our issues. I don't have issues. Okay. But anyway, Om, what were you doing? Uh, I found a butterfly. You found a butterfly down by the pond? Yep, it was beautiful. Well, that's very nice. That's very nice, Om, but I'm glad you're here today. Me too. Okay, let's take a look at some multi. So today in this second video, I'd like to take a look at some tangent surfaces, tangent objects that we're going to encounter. Multi is about derivatives, and tangents are important for us. So we'll be looking at tangent lines, tangent planes, tangent spaces, tangent surfaces in general, and we need to know how to describe those. And a lot of that comes from your linear algebra when you take linear algebra. So a lot of this is review, but some of it is not. So let's just take a look at some of it. So we'll be looking at equations. Let's begin in R2. So in R2, our objects are going to be curves, and so we'll be looking at tangent lines. And so we only have lines to deal with here. But we can deal with lines in a couple of ways. We can deal with lines using Cartesian coordinates, x's and y's, or we can deal with lines parametrically. Just this a little bit. So we can look at these lines parametrically. And that's basically it. So let's take a look at that. Cartesian. Y equals mx plus b, or y minus y naught equals m times x minus x naught. There are a couple of others, but these are the main ones. This is the slope-intercept form. And this is the point-slope form. So to use this one, you need the slope and an intercept. For this one, you need a point and a slope. This one is more useful to us because we will have a point on the curve and we will be looking for the slope, something that you did in Calc 1. And I put this up because this is canonical for how things work in higher dimensions too. Parametrically, these are functions, or I look at them as functions. So a line, it'll be a one-dimensional object. A line is a one-dimensional object. We'll need one variable to describe it. So you will need a direction, and that direction will be a direction in the plane. So a vector might be a unit vector, it might not. T times the direction plus a point. And a point is a point on the line, so these are both vectors in the plane. Parametrically, this is a line, and a line in the plane. So this is what these will look like. On Monday, we'll do examples of these and many others. I'll give you a bunch of stuff to find, just so we can get familiar with finding equations of our tangent objects. So that's it in the plane. We get a little bit more when we get in 3 space, and we get a lot more in 4 space, and even more. Well, let's do the 3 space first. So in 3 space, the easiest place to start are planes. The easiest place in any Euclidean space is one dimension down. So these guys will be the easiest for us to find, and we'll first of all find Cartesian forms. And again, there are two. Y equals m1 x1 plus m2 x2 plus b. This is the slope-intercept form again. So let's see, I brought my plane here again. Thanks, Snow. So here is a plane, and a plane has, like an airplane, has two slopes, a pitch. Well, a pitch is actually toward you in this direction, a pitch and a yaw. A plane has a slope in the x1 direction, that would be like -1, and a slope in the x2 direction, maybe that's 2, and then an intercept where it intersects the y-axis. So two slopes, pitch, yaw, and an intercept. So these are all numbers. Slope means what it usually does, rise over run in this direction, rise over run in this direction, and intercept means what it usually means, where it intersects the y-axis, slope intercept. And it's got another one, y minus y naught equals m1 times x1 minus x1 naught plus m2 times x2 minus x2 naught. And this is the so-called point slope form. The point in this case is the point x1 naught, x2 naught, y naught, y naught. And the slope is really slope s. It's got two slopes, pitch, yaw. Slope in the x1, slope in the x2. So the Cartesian form of planes in 3 space is easy. It's like this. The Cartesian form of spaces in 4-dimensional space is almost the same. You just have one more term, an m3 x3, and down here you'd have one more term involving x3. So this is why, starting with 1 dimension less than the home space, these are fairly easy in Cartesian coordinates. So I hope we're kind of good with this. Let's take a look, and we'll practice on Monday. Let's look at the parametric form of planes. The parametric form for a plane, P for plane of, now you need 2 parameters, an S and a T. And although we're doing it in 3 space, this is what a plane looks like in any space parametrically. Parametric has some big advantages in terms of things always looking the same, no matter where they are. So P will have, if it's a plane, you're going to have an S and a T. This time you're going to have 2 directions, dir1 and dir2. And you need a point on the plane. So here is the point direction form. Of a plane in 2-dimensional space. We need one more thing, and we need dir1 and dir2 are linearly independent. If you have 2 directions, 2 vectors, these are vectors. If you have 2 vectors that are not linearly independent, that means one is a multiple of the other, or they are in the same direction, in which case this would, no matter, even if you have two parameters, those parameters don't separate that direction. So this would be a line if they're not linearly independent. So the linear independence is important in actually getting you a plane. And this is going to generalize in higher dimensions as well. And this is it. The planes in R3 or in any space always have the same form. Now, there is another one here, other than parametric, and these are the vector forms. And these end up to be important for a number of reasons, not just in 2 space, but in 3 space, but in higher spaces. So in this case, the most important vector form is called the point normal form, and it's of the form vector x minus x naught dot n equals 0. So this uses the fact that 2 vectors are perpendicular if and only if their dot product is 0. So any vector in the plane minus x naught dot n is 0. So why does this work? Well, if we take our plane and we take a point x naught on the plane here, and then we take any vector x in the plane over here, x, that represents any vector. And we look at the vector x minus x naught. This is the vector that extends from x to x naught, from x naught to x. So here is x minus x naught as a vector. And notice then that this vector, I will escape for a second. That vector, because it lies in the plane, will be orthogonal or perpendicular to n, this pen is n, that is perpendicular to the plane. So the vector x minus x naught, not x itself, not x naught itself, but the vector that lies in the plane is perpendicular to n, and that's true no matter what x we pick. So if you pick any x in the plane, the vector between that x and x naught is perpendicular to n. That's the geometry of this point normal form. One of the things we want to do is, if I give you the point normal form, find the Cartesian form, find a parametric form, go back and forth between these forms, because sometimes it's convenient or even very insightful to use one form rather than another. And we'll actually see really good examples of that. So maybe this is the only vector form that I'll give you right now. So that's it for planes. So let's try lines. So we want to look at lines in 3-dimensional space. And here, probably the easiest is the parametric form. The parametric form of a line anywhere is the same. L of t is t times a direction, and there's only one, so dir1, plus a point on it. So this is the parametric form of any line anywhere is this. So in any case, in this case, what you need is the direction of a line and a point. And so if we have 3 dimensions or any number of dimensions, we take a point on, so that's the point. We take a direction of the line, This is a vector, which is the direction of the line. And then if we look in that, starting at this point, if you look in this direction, any distance, the t is scales it, so it gives you any distance. If you look at any point, no matter how far it is, as long as you're looking in that distance, you get a point on the line. And you can even look in a negative way. So this is why this describes a line in the plane or really, or in 3 space or really anywhere. Okay. So maybe number 1 is the Cartesian form of a line. And this looks different in a way. It looks like this. x2, let's have x1, x2, x3. So x1 minus x1 naught divided by a equals x2 minus x2 naught divided by b equals x3 minus x3 naught divided by c. So this is not an equation. This is a Cartesian form of the line. It really involves 2 equations that are linked. So you could say it's 3. This equals this equals this, and this equals this. But by transitivity, if this equals this and this equals this, the thirds are also equal. So this represents 2 equations that are linked together. And so this is called the Cartesian form of a line, and any points x1, x2, x3 that satisfy this give you points on that line. So on Monday we'll talk about how to go between the Cartesian form and the parametric form and vice versa. And the basic idea is set this value. This doesn't have to be a specific value. These only have to be equal. So set this value equal to the parameter t and solve for x1, x2, x3. And that will give you the parametric form. So there is a link between these. So let me talk just a little bit more about what happens in higher dimensions. So in R4 or R5 or R6 or in general Rn, and I just want to talk about the parametric form here. For lines, the parametric form is L of t equals t times a given direction plus a point on. That always describes a line. The direction, though, is in Rn. So the direction is a vector from Rn, so it has n different components, x1, x2, up to xn. And the point also is a point in Rn, so it also has n different components. A plane is p of 2 variables, s and t, is t times dir1 plus s times dir2 plus a point on it. So it's almost identical to line, except one more direction. And again, to be an actual plane, you must have linearly independent directions. So dir1 is linearly independent of dir2. And moving up in the world here, we can also have a space, a 3D space in Rn, as long as n is bigger than or equal to 3, or let's say 4. In which case, the space of S and T, and I'll need one more, say U, is equal to S times dir1 plus T times dir2 plus U times dir3 plus a point on it. And this time, the set of directions must be a linearly independent set. So this must be a linearly independent set. No one of these is dependent on any of the others. And that's because if they're linearly dependent, then you will get at best a plane. So this is the way it goes. In general, we could look at hyperspaces in Rn as long as n was bigger than or equal to 5, and so on. So the homework for this time will consist of moving back and forth between these various types of equations. And we'll do a worksheet on Monday where we do the same thing, have some fun with these equations, find some lines and planes and normals and that sort of thing. So that's it. Hope you have a rest of the good weekend, and we'll see you Monday.